digital salmon project, but today I'd like to talk a little bit about the kind of generalized view on the metabolic modeling using the focusing on the careful formulation of the energy metabolism. And the idea of this comes from the textbook's knowledge that all the metabolic units in the architecture of the metabolism are interconnected between each other via energy equivalent or the redox equivalent substances which are turned over. And they are in certain case or in certain formulation can be used as a pacemaker because they are harmonizing the rates of the catabolic activity with anabolic activity and overall with the growth. So that's why the formulation of the energy metabolism is very important for that. And sometimes this topic is challenging, but this can be solved even on the level of the stoichiometric models. And for example, like here on this example of the stoichiometric model of Escherichia coli, so the 135 transformers are already sufficient to formulate all these details of the formulation of the energy metabolism for anaerobic and aerobic conditions. So overall, the turnover of the energy substances can be considered in this a bit complicated view. So there is processes of the ADP phosphorylation via, for example, glycolysis or respiratory chain, and of course dephosphorylation via metabolic reactions or reactions of maintenance. But also there are the processes of MAP de novo synthesis and degradation and using of ATP as a substrate for the polymerization into RNA and DNA and corresponding degradations. All this turnover of this AXP pool, so adenylat pool, is taking place on the different time scales. So there are fast reactions and slow reactions. And then depending on the purpose of the modeling, so either the dynamic equilibrium between all these XP forms can be taken into account, or only the couple of them, ADP, ATP, if we talk about the steady state conditions, can be taken into account. So I have different examples for the modeling of the XP balance on the dynamic scale and on the steady state approach. And today I'd like to focus more on the steady state approach because there is a certain architecture in the energy substance turnover, which can be presented in terms of the loading reaction and regeneration reaction. So the ADP can be converted to ATP via glycolytic, for example, activities, and then via metabolic activities dephosphorylated back to ATP. So there is always turnover of the ATP, ADP. But since ATP is not accumulated in the system, so it's continuously under this turnover. So that's why this simple relationship between the loading and regenerating reactions can be kinetically presented in this sense. So that from the point of view of the concentration, if the perturbation is occurred, so then the G2 homeostatic regulation, the system turns to the previous steady state. And these are the rate profiles for the two of these reactions. And this very simple presentation of the energy metabolism can explain the homeostasis as an ability of system to sustain the steady state through the system, and also adaptation, that the kinetic properties of each of these reactions can change the steady state which is achieved by the system. So, but most important that at steady state conditions, so that's what we use as an assumption for the stoichiometric modeling. So we can consider ATP, ADP as a conserved moiety, because under dynamic condition this is an open moiety when the ATP is degraded or synthesized de novo, so the pool is varying over the time, but under steady state condition this pool is constant. And so if we use this approach as steady state with a conserved moiety of ADP, ATP, then additional view which needed to be taken into account is that there is a competition of the pathway for the ATP. So because the ATP is highly interconnected in the different metabolic reactions, and for example, in microorganisms which can metabolize ATP or synthesize ATP via glycolytic phosphorylation or via oxidative phosphorylation. So there is a competition between two of these pathways for the ADP as a substrate. And then depending on the environmental conditions and the efficiency of each of these processes, the system takes a scenario which is already exist in the network, but it is ruled by the environmental conditions and also regulation. So, and this system can, this very simple example of the energy metabolism can explain Pasteur effect and Crabtree effect. So in the system, so when something is happens in the environment of the system takes place either this scenario or this scenario. And this approach I like to exemplify on the modeling of energy metabolism of Arabidopsis on the assumption of the steady state growth. The general idea of this metabolic efforts was done on this with the aim to understand the effect of the sucrose transporters in order to, in future, try to use the manipulation with the sucrose transporter to change the phenotypic appearance of the plant. So how the sugar transport can change the phenotypic traits of the plant. But for that we need to model in details the transport of sucrose from source cells, so from the leaves, we the phloem to the sink, to the root cells, for example. So for that we use the formulation of the multi-compartmental formulation of the plant. But important to know that in Arabidopsis there are the three types of the sucrose transporters. So two of them are proton symporters and one is an efflux transporter. So since they differ in the nature, so we would expect that they might have a certain correlation in the transport system of the plant, but nevertheless, if you look to the expression profile of these transporters in all tissues of Arabidopsis, you find that they are nearly presented in all fractions, or in all tissues of the plant. And the reason for that is that there is organized transport system of the sucrose from the source tissue to the root tissue. We are companion cells with a number of the loading, with a process of loading via apoplast to phloem, and then unloading via apoplast to the root cells. And the loading is organized with a combination of two transporters, so efflux and then proton symporters. So that's why it was important to formulate the formation of sucrose and energy metabolism in leaves, and then transport of sugar down to the root, and also formulate the metabolism of the root and formation of the biomass. So that's why finally we came to formulation of this scheme. So we have an autotrophic leaf and a heterotrophic root. So we have a phloem which plays the role of the transport compartment, and then intermediate compartments of apoplast, which are acidified by the proton pumping from the neighboring tissues, and then allocation of this effluxer and then proton symporters in these directions allows to direct the sucrose flow from the autotrophic leaves to roots. And so in the backwards we organize, or we model the movements of water and nutrients from the root up to the leaves. And the motive force for the efflux or for the sweet transporters are sucrose gradient, so that goes according to the gradient, and motive force for the symporters family soup, so it's in the proton gradient, so that goes in this direction. So finally, additional constraints which we have to take into account is also the conditions regarding to the light. So in the daylight, plant produces starch, which is accumulated in the leaves, and in nighttime the starch is used as a carbon source to keep on growing. So that's why we have taken in account two scenarios, so daylight and the night light. And under these scenarios, the carbon source and the energy source for the formation of the primary metabolites are different. So either it's in the light and CO2, or it's a starch and so the energy reserved in the starch. And of course, there is some possibility to compare finally the outcome of the model with the phenotypic mutants which are already produced, and for them is known some phenotypic traits. But nevertheless, so the first step is just to develop the model. And for this, we had to formulate very carefully the interaction between the different compartments in the leaves. So because there is a plastid, which is producing trioses, and trioses are exported to cytosol for the synthetic activities, but photosynthetic system is presented in the plastids, and also carbon cycle. But these processes is resulted in the production of NADPH and ATP, and the question arises whether the production of own production of ATP in plastid is sufficient to support the activity of a carbon cycle or not. So, but it's also very well known that in plants there is a pathway which is called malate-aspartate shuttle, which is transferring the reduced equivalents from plastid via the exchange of malate and oxaloacetate to mitochondria, where it is used for the oxidative phosphorylation. And then it uses for the production of ATP, and ATP can come back to the cytosol and then finally be transferred to the plastid. And on the level of this model, we wanted to test whether this scenario is plausible or not. So, but in order to formulate this, we also need to formulate very carefully the growth of biomass or formation of biomass, because it also produces NADH, which is uptaken by malate oxaloacetate shuttle to mitochondria. So, and then to test this model at the different conditions, presence of the light or the night conditions. Finally, we developed the three-compartmental model, which consists of mesophyll, root, and the phloem, and several subcompartments in each of these in each tissue. So overall, we had 400 transformers, 413 balanced compounds, 41 pathways, and nearly 750 genes are annotated for this model. So into this model, we have taken only those metabolic reactions which are contributing to this formation of the primary metabolites and formation of the biomass. So the secondary metabolism of secondary metabolites was not taken in account because it doesn't contribute to the mass formation of the plant. And after rigorous topological analysis, optimization using flux balance analysis, we came to the formulation of the network, which is having an overall total degree of freedom 16, and conserved moieties in all compartments was around 24. So, and this model was more or less easy to constrain because using the ratios taken from the experimental values. So that's why we found the solutions for these flux balance analysis, which are very close to the experimental values. But nevertheless, so that the flux balance analysis shows us that under the light condition and the night condition, so under major constraints, which we know from the textbook, that consumption of the, let's say, or absorption of the light, production of the starch, consumption of CO2, of water, and protons, etc. So this is in light conditions, so the flux balance analysis has caught this scenario, and also for the night conditions, that prediction of the flux balances was correct. And when we compare the results of predicted by the model with those which are published for the plant, they nearly match. So, for example, this is ratio between consumption of the absorption of photon and CO2 consumption. So this is a model, and this is what is published in literature based on these are experimental data. So, and the different aspects of the model which are predicted actually very close to that what is measured in experiments. So that's why we have a ground to say that our model catches the processes we've been focusing to more or less adequately. So, and the major problem comes from the possibility that the photosystem or photosynthesis can be run in two general modes. So the cyclic electron flow, when the protons are pumped to pump out, and the ATP uses it without the formation of NADPH. So the cyclic proton electron flow and non-cyclic electron flow, which is where the formation of ATP and NADPH are coupled. So, and formulation of the photosynthetic system using these two scenarios allows us to estimate the ratio between two of these processes, and also under the constraint of the ratios between photorespiration and photosynthesis, taking this as a constant. So we run the flux balance analysis on the different ratios of the cyclic and non-cyclic electron flow, which shows us the turnover of ATP and ADPH in the plastids, and shown that under experimentally observed ratios of ATP and ADP, so which is around 1.4, 1.5. So the system must to export ATP from cytosol and import NADPH via the volatile shuttle to mitochondria. So if we change this ratio between cyclic and non-cyclic to the, let's say, to the high values, so then we go, so the prediction of the model turns upside down. So, and finally, based on this developed model, we could understand that in the light conditions, so the fixation of CO2 yields triosis. We are Calvin cycle, and to run efficiently Calvin cycle, the ratio between ATP and ADPH is required to be 1.5 or greater. But the photosynthetic system actually naturally produces the ratio 1.2, so it means that the extra ATP has to be taken from cytosol, and excess of NADPH has to be sent to mitochondria for synthesis of ATP, which turns back to the system, so to the plastic. And these exchange rates is very difficult to measure in experiments, but at least from our formulation of the model, this scenario is predicted. And the same model actually shows us that in night conditions, when the photosystem is off, and also the malatoxylate shuttle, which is light sensitive, also off, so then the redox balance in plastic is fulfilled only via pentose phosphate pathway, and the ATP is 100% fed from mitochondria. So, and then it forms sufficient ratio for the formation of the running the processes, which is typically occurring in the plastids, like a reduction of nitrates, sulfates, etc. So not only the formation of trioses, because under night conditions, so the starch is degraded to glucose, and glucose is degraded to triosis in cytosols, not in the plastid. So, but nevertheless, this functioning of plastid in nighttime was also involved the redox potential of the plastid itself. So using this model, we finally could reconstruct the balances of the protons in each compartment, so leaves, phloem, and the root. So, and measure contributors to that, so who is producing protons and consuming protons, where they come from. So, for example, like nutrients are usually come in symport with the protons, and so there is also protons pumping out, so there is a balance of the proton in and out. So the proton is also can be exchanged via upper plus due to the ATP pumps. And so that for the post scenario, for the light condition and dark condition, we could reconstruct the fluxes of the sucrose, and it corresponds to, it matches to the fluxes of the proton, and also the major contributors of the proton were reconstructed. So this is nearly genome scale model, but nevertheless it was reduced only for those metabolic pathways which are contributing to the formation of biomass, and the estimate for the growth of biomass under light condition and night conditions were estimated. So, and coming back to my current project of digital salmon, so we are heading to towards the modeling of the...
Sorry, we are really over time.
Over time, yes. Okay.
Okay.
So then I stop at this point.
Okay, yeah.
So let's thank the speaker.
One very, very quick question, if it is. If not, let's move to our next speaker. Yeah, thank you.